So let's try to understand how much data is out there in the world. It was estimated that the amount of data in the whole world in 2018 was 18 zettabytes. That is 18,000 exabytes. If all the data was placed on a CD-ROM and stacked up, they would stretch to the moon in 75 different piles. Back in days, we used to have one CD-ROM, and we used to think that it got so much data in it because we were using floppy drives and then the CD-ROMs. But now the whole data, just like it's in such a massive quantity that we cannot even expect. Now, why we are discussing this today? Why not we haven't discussed this in 1990 or when the computer science was started? So let's go back. Hard drive cost per gigabyte in 1980 to 2009. So this is the price of it, yeah? Storage is becoming cheaper and cheaper. Why and how? We all know that. So in 1980, it was for $1 million. That's what we meant to spend to buy the hard drive, yeah? Now, with the passage of time, you can see the price is keep coming down. But similarly, the data is going up. Currently, the hard drive, if we talk about in 2010, was costing only roughly 9 cents. That's how cheap it was. 1 GB we are talking about over here. 1 GB in 2010 was for only 9 cents. And 1 GB currently you can get it for like free because people just wanted to get rid of it. So this is why we are discussing this. We got cloud computing now. We got more data. Now, on the other side, computer power of commodity processor is increasing. Before, our processors were like very slow and they could not do logical computing at the same time. And it was impossible for computers to do multiple processing at the same time. So this is the data from 42 years of microprocessor trend data. So if you see on the left side, you have 10 raised to the power 0 up to 10 raised to the power 7. 1970 to 2020. On the right side, we have number of logical cores, typical power in watts, frequency, single thread performance, transistors in thousands. So if you see up until 2005, there was not so much on number of logical cores, and all of a sudden there was an increase. Whereas you can see the increase in this trend. And now we have 10 raised to the power 8 roughly over here. So this is the power of the computer, which is keep increasing. And we still don't know where it will stop. We have capacity to store huge volumes of data. We also have cheap computing power to process huge volumes of data. Faircast and Google flu spread prediction would not have been possible just a few years earlier, because before that we never can imagine to buy such a high volume of data and compare it because it was very expensive. It is like normal data, only bigger. Partially yes, but there was other considerations too. Now, how big is the big data? It's so big that currently used database technologies cannot cope with its size. And current storage system needs horizontal scaling. In 70s and 80s, 1 GB was big data. In 90s and 2001 terabyte was big data. Currently big data is 1 PB and beyond. We don't know, because when we talk about the data which is Google is using, it's like massive. We need like size of the football stadiums just to keep the processors over there. Storage capacity of hard drive have increased massively, but the reading speed have not kept. A typical hard drive in 1990 was 1370 MB and the transfer speed was 4.4 MB. Time required to read the whole drive was 5 minutes. This was when we used to have a hard drive. And then we have the HDD, which is SATA hard drive, which was like 4 terabytes. Transfer speed was 200 megabyte per second. The time to read the whole drive was 5.5 hours. I still remember when I used to format my hard drive, it usually take 5 hours to format. Reading large volumes of data from a single drive is getting slower and slower. We need to add more drives and read data from them in parallel. That's where the parallel computing comes in. Like a normal data, only bigger in the size of volume. And more diverse database records, XML documents, text documents, flat files, PDF. We call them variety. And is generated as a faster rate than before. We call it velocity. 3 V's of big data: velocity, variety, volume. So if anyone asks you what is volume, that means we are talking about the normal data, the size of the data. If anyone asks you what is the velocity of big data, that means how fast the data is processing. And if anyone asks you variety of data, that means what data we are talking about, like XML document, text document, pictures, PDF, etc. Facebook uses 4 PB of data per day, and that's a volume. Status can contain tax images, location, tax friends, variety. Around 2.2 million likes and comments per minute. That's velocity. How quick is processing? That's velocity. What is processing, like image, tags, whatever, that's variety. And how much data we are talking about, that's volume. Same with Twitter. 12 terabyte of data per day, that's a volume. Each tweet is 140 characters of text, but can contain videos, links, documents, etc. And that is variety. 350,000 tweets per minute, that's velocity. Now, other definitions of big data. Big data technologies describe a new generation of technologies and architecture designed to economically extract value from a very large volume of a wide variety data by enabling high velocity. Captures, discovers, or analysis. This is the definition provided by the International Data Corporation. And we call it 4 V's of big data. Earlier we discussed 3 V's of big data, which was value, variety, and velocity. In this one, we have volumes as well. And yet another V, veracity, which means the noise and abnormality of data. Data sets whose size is beyond the ability of typical database software tools to capture, store, manage, and analyze. Another definition of big data is big data is where the data volume, acquisition velocity, and data representation limits the ability to perform effective analysis using traditional relation approaches or requires the use of significant horizontal scaling for efficient processing. Another simple definition of big data is where parallel computer tools are needed to handle data. Because the data is so big, we need parallel computing. Now let's discuss the properties of big data. So, rawness, immutability, perpetuity is the properties of the big data. Now, what is rawness? We should store the rawest data that we have. The rawer the data is, more information we can get from it. For example, keeping track of Facebook friends, number of friends, list of friends, unfriends events. What time you have unfriend a friend is known as event unfriend. What do we mean by big data immutable? We do not update the data. We only add more data. If you update the data, you will lose your previous data. Ensures human fault tolerance. No data can be lost due to bugs. If bad data is written, good data still exists in the system. Easier to manipulate. If you remove the data, you won't be able to fix it. But if you just add more data, it will be easier to fix. That's sometimes we call recovery in our PC. Big data is eternally true, a consequence of immutability. Once the data is in the system, it's always true. Now let's understand student database. So we have ID, we have name, gender, course, status, town. So 4 entries we have. Each ID may have one name and that will associate with gender, course, status and town. Or a name will be associated with the ID and other details. But what happens if Jane changes her town to Dundee, for example? Because Jane is changing her town, if we add data, like previous town was Liverpool and new town is Dundee, that means we adding a data. But if we overwrite this data, we won't come to know that what was the previous town of Jane. We now have correct information, but we have lost some previous information because we have overridden. Now, what if we do this way? We create timestamp. So this data was created on this, which was associated with this. This was associated with degree, and same time spent was distributed to this. But what happens if Jane changes to her town? In that way, we will add that on this timestamp, Dundee was added for Jane. How is big data changing our world of thinking? Analyzing whole data set instead of just samples. Loosen up requirement for the exaggerate of data. Shift from data telling us why something is happening to what is happening. Reuse of data. Use whole data sets. Until recently, most of the science relied on making conclusion about large data sets by using samples. But in many cases nowadays, we can process the whole data set. Requires ample storage and processing power. Cutting edge tools to analyze data, easy and affordable way to collect the data. Back in days when we need to do any test, we just take a sample of data. But now we can do whole data because it's easy, it's quick, and it's not so expensive. Fraud detection relies on detection of outliers in complete set of transactions. If you miss one fraud, it can impact whole bank. So that's why you need to analyze complete data. Recommendation system also rely on looking at the complete set of metadata about transactions viewings. Now, what do we mean by living with the data? When we were dealing with small samples, we had to make sure each data point is accurate. We went to great length to make sure that we had exact. In the world of big data, we have to allow impression. More thumbs better. Messiness is making its way into many areas where large volume of data was stored and analyzed. Image classification databases. Now, when we talk about data, we have to discuss structured data and unstructured data. What's the difference between them? Structured data means defined data type, like rows in relational database. Unstructured database mean text document, PDF, images, videos. But we also have semi-structured data, which means textual data files with a discriminable pattern that enables parsing, like JSON model, XML model. Quasi-structured data. Textual data with erratic data format that cannot be formatted with efforts. Relational database deals with structured data. Big data analysis deals with all kind of data. Automatic language translation. We can teach computers all the linguistic rules required for translation between two languages. This was tried in 1960 and proved to be failure. Or we can let the computer use probability to calculate which phrase in one language correspond to which phrase in another language. We need to train the model on lots of data. At first, a smaller set of perfectly accurate translations were used for training, but then in 2006, Google Translate came into light. Idea use every translatable available regardless on how correct it is. Much more data than used by IBM, but data was much less accurate. The result far outperformed IBM translation system. Why instead of what? Human brains intuitively look for causal relationship between events, the questions of why. But causal relationship are often very hard to establish. In big data world, we are looking at correlation relationships, two or more events occurring at the same time, or where one event is usually followed by another one. Strong correlation between events tell us that there is a high probability of two events occurring at the same time. This is how recommendation system works in Netflix, Amazon, etc. How Amazon recommendation work? Initially, Amazon employed expert to write book reviews, recommendation, etc., which was very costly. The first automated system for recommendation looked for user with similar profile. Assumption similar profile of users would want similar books. The recommendation system that followed abolished this idea and looked just a correlation between purchases of product. What? Which was more successful? We have to be careful about correlation. So in this example, we have number of people who died by becoming tangled in their bedsheet. which is very unlikely event. But how many? When we do the data, we will realize that there was 800 deaths. So this was from 2000 to 2009, 10 years of data, from 200 death to 800 death. And this was the size of the person. So we wanted to understand if the size relates or correlates to their death. We also trying to understand what is per capita cheese consumption. So does that really makes any difference? If anyone taking cheese can die by bedsheet tangling? So if we see the data, the black line is bedsheet tangling, whereas the red line is for the per capita cheese consumption. So is there a correlation? Because the lines are surpassing each other, there may be a correlation. Use of data for purpose they were collected for. Transaction of purchase in online shop, search term in search engine. Many of the data would be discarded once they serve their primary purpose. But there is a lot of hidden value in the data. And we now have capabilities to store and process big data. For example, if a family keep buying bin bags at the same time when they buying the toilet rolls, is there is a correlation? There is no point of losing that data. If we keep collecting that data after 10-20 years, we can be easily correlate whether to understand they both correlate or no. Now, what do we mean by big data storage and processing? So we have no SQL databases and we have distributed computing. No SQL databases, similar data model than relational databases. Stores data as object with attributes. Objects do not need to have the same set of attributes. Allows flexibility in data storage. Whereas distributed computing, data and computation distributed over a number of commodity servers. Horizontal scaling, adopt map reduce. Later in this video, in this complete guide, we will learn NoSQL databases and we will also discuss distributed computing. Where is big data analytics used? Amazon is one of the best one. Many, all the data which we get from Amazon or any data which Amazon uses, finds from online, they uses that. Netflix is another one. Walmart is the third one. In UK, we have Asda, Tesco, all these companies, they all use data. For fraud detection, we have MasterCard, Visa. These are the two companies. We have healthcare professionals, we have sports, we use big data everywhere. Now, what are the myths and misconceptions about big data? There are loads of myths. People don't understand what is big data and they just keep getting confused and making other people confused. Data science is completely autonomous. Data science usually requires a skilled human to set out the problem and interpret the solution. Data mining lets computer to do best. Dig through a lot of data. This in turn lets people to do what best to do, which is to set up the problem and understand the results. All we need for data science is lots of data. It is equally important to have the right data. Data science is easy. It's just a normal data analytics, but on bigger data. Data science pays for itself quickly. Sometime analyzing the data won't reveal any hidden value.